Hello. First, I want to introduce myself. My name is Oscar Hernandez. I work at Oak Ridge National Lab, and there I am in charge of the programming models for the next generation systems that we will have there. So as you can guess, it's a very challenging job because with the new trends of the new systems that we're getting and how the industry is evolving for exascale, we're kind of like looking for what's the next programming model that we want to start to use. And basically, we're looking at new ideas. We are very hopeful in the support of OpenMP for exascale. And the more we see is the better the new features that we see in OpenMP 4 are starting to become very interesting to us. And we see that OpenMP 5 is going to be something that is going to be really, really interesting, and that could be a programming model that we could use portably across different systems. So for today's talk, I'm going to focus a little bit on our experience on accelerator directives, and especially in the technology that we have been using at Oak Ridge, which is Open ACC, and what are our plans for transitioning from Open ACC to OpenMP 4, and what will make us more comfortable to do that in the future, in the near future. And then we're going to give you some experience that we have about the directives, how we're using them, and basically how to map from OpenACC to OpenMP 4, and what features are very straightforward to do, and what things are missing, and what are the challenges that we see when we start to evaluate the directives. So I will go for my next slide. So this is kind of like the landscape of the supercomputers. We're seeing an immense number of parallelism in the node. And as we move forward, we're moving more to heterogeneity. For example, we started with Titan, and which is a 27 petaflop theoretical performance. And then we're moving to our next generation of system, which is Coral, which is called Summit, which is about 5 times to 10 times faster than Titan. We're still looking at heterogeneity in the system. And this heterogeneity aspect that we're seeing here is probably going to stay with us for some time. So basically, what the challenges that, we have 5 years of experience of working on Titan, and we develop technologies there for help our applications to port, to exploit things in this new system. But as we move to Coral, things are getting more, the complexity to the user is becoming more challenging. And as we start addressing things with directives or programming models, this is something that we're looking forward to see in terms of open and directive-based programming, in terms of OpenMP, to see if we can help the user manage the complexity of programming these systems. So as a result, we have put a lot of emphasis or a lot of resources in terms of OpenACC and OpenMP 4. So why do we want to, the challenges that we're seeing, for example, in program these next generation systems are, these 5 challenges, where parallelism, heterogeneity, how we're going to deal with the memory hierarchies, resilience, and power. However, the immediate challenges that we see with the accelerator directives is how to achieve portability. So right now, for example, we have this system that's based on GPUs, and we have systems based on Xeon Phis at other labs. And how can we write codes that are performance portable across these 2 different systems, and can the directives really help us? And that's really, really important for us, the portability aspect, and because that's going to help us to maintain the applications, make the applications more easy to program, more maintainable. Application scientists are going to become, are happy to see that their codes are not without too many restructuring of their applications. If they can still achieve portability, that would be great. And then we have a lot of industry and resources that our goal is to see if we can go in that direction. Currently, we have the programming model that most of our applications uses is MPI plus X, but we're starting to see that in these next generation systems where, in some cases, some of the nodes are getting more powerful and cost of moving data is becoming more expensive, we're starting to think that maybe in the future we're going to start seeing more of, instead of asking MPI plus X, is maybe OpenMP plus X, where X can be a PGAS model or communication as a communication library or an exascale runtime. And this may help us to really, if OpenMP can help us to manage the complexity of the nodes, that will be very good. But at the same time, we have to think about the future. And OpenMP needs to evolve to allow to exploit all the characteristics of the node. And because of this, we see that the exascale programming environments are starting to emerge. And a lot of experiences will help us to drive, at least in the case of our system, Summit, will help us to define what we need for exascale. And during this Coral timeframe, where we're going to be working towards OpenMP 5, we have to think about those challenges and what things we need to address there. So one of the things that we are starting to look in the applications is that we're trying to look at this aspect of portability, and we need to find models that can help us to write applications that are architecture independent with very high level constructs to represent data or word decompositions. Some people are working in this area at the different labs using DSLs and so on. And then we need, for example, one aspect of the application that needs to be lowered and into something that is adaptable and portable. And this is something, area of research that has been explored in terms of exascale runtimes that we have seen. But this is still in the research areas, and there's a lot of lessons that we can learn. And ideally, what we want is to reduce this complexity of managing all these different resources in the nodes so that it can help make the application more easy to program, but at the same time being portable across architectures. And then we have the area where we map the parallelism to the architecture, and that's where we use something like, for example, OpenMP, where we started to optimize more towards an architecture. And one thing that we're seeing is that OpenMP is helping us to generate the code that we need for these different accelerators and Xeon-Phis. It has the capability to be tunable, but at the same time, it has to become more smarter. And maybe there is some lessons that we can learn from, for example, the research on exascale runtimes so that we can adapt new features in OpenMP. For example, Eric's talk that talk about all these tasking and priorities on tasks, all those things that make the runtime scheduling more efficient, that's sort of things that we need. And then we want to see how, what features do we need in OpenMP to support, to support more high-level constructs for parallelism, but at the same time, keep OpenMP in a way that can be tunable to get the performance that we need. And the key thing here is, can we make the application programmer's life easier? Is it possible? And if OpenMP can offer us that as it evolves for the future. So we started with directive-based programming. Directives was a key strategy for us. It was started when we put the RFP for Titan. We wanted to find a programming model that was easy to program GPUs. Because of the time to deliver the Titan, we needed a directive-based programming model that worked very fast and basically was available to our users. And that was the main origin of why we have OpenACC. However, going to the future, we want to move forward into something more standard like OpenMP 4, where we start seeing more support on compilers. And this is something that encourages us so that we can move our existing applications written in OpenACC to OpenMP 4. We have still a large community of users, of OpenACC users in the lab, and most of them are there because compilers are a little bit more mature for GPUs, for supporting OpenACC on GPUs. But the transition, we're starting to move to ask the applications people to move to OpenMP 4. And that transition will happen as we get better compilers to support OpenMP 4 on GPUs. And to do this, we started to understand what does it take to move OpenACC to OpenMP 4. And what are the technical challenges, if there are any, and basically, and how can we achieve performance portability with OpenMP 4. And those are the main things that we would like to talk today. And the main differences when we are starting to convert our applications with OpenACC to OpenMP 4 is that is this aspect of the philosophy of the directives, one being descriptive versus the other one being prescriptive. So there are certain choices, for example, in OpenACC, certain directives that that the compiler chooses, what's the best way to translate into the GPUs, where in OpenMP 4, we may need to ask the user to make some of those choices to translate them efficiently to the architecture. However, we still need to understand what are those choices based on the implementations of OpenMP 4 and to see how we can map one to the other programming model. Many of the constructs have one-to-one mappings. We can think about something like OpenACC is kind of like writing OpenMP 4 in terms of OpenACC is kind of a little bit like lowering OpenACC to OpenMP, although so where you can do certain choices on how you're going to distribute the work across the different units in the GPU. Some constructs are present in one programming model and not in the other one, but both these two are starting to get very close to each other, making it easy to move from one to the other one. At some point, there are very subtle differences. Basically, it's mostly the freedom in the compiler on how to map the parallelism into the architecture. And in OpenMP 4, the user has more control over how to do this. This is just a slide summarizing what we are seeing in OpenMP 2.0 versus OpenMP 4, and we start to see that most of the directives supported in OpenACC are also supported in OpenMP 4, or are part of the OpenMP 4.1 draft, and that definitely will make things easier to move. Still, there are certain directives that are still not supported in OpenMP, like the cache directive or the tile directive. And these are things that maybe it could be something useful for performance, and perhaps it could be something useful for OpenMP 5. Right now, we're just kind of like relying on smart compilers to optimize for the memory hierarchies. And we hope that we will get good compiler implementations to do that so that we can get the performance. The challenge mostly is trying to write portable code with this new set of directives and seeing how we can translate the different directives from OpenACC to OpenMP 4. So, so we developed some guidelines on how to do that. The process is not as complicated as we thought at the beginning, and I'm just going to go through it one by one. Yes, go ahead. So this is where, I'm going to talk a little bit more about that, but this is where parallel loop in OpenACC is a little bit descriptive and leaves the programmer, the compiler, the choice on how to map the loops, basically on gangs, vector, or workers. And in OpenMP 4, yes.
Yeah, what he's talking about is the fact that parallel target and parallel teams both map. So in OpenACC, parallel is target and teams together.
Yes, yes.
But yeah, then also when you're talking about loop, when you say loop, what you're saying is this loop is independent. And that's all you're really asserting. We haven't told the compiler anything else about what you want to do with it.
Yes, yes. So basically, there is this different choices. So since we have now a better mapping between OpenACC and OpenMP, the question is, when can we transition our applications? And mostly, the transitions is going to depend on the compiler implementation. Right now, we're starting to get OpenMP 4 compilers for GPUs. And once we start experimenting a little bit more with the OpenMP 4 compilers and getting the same performance that we're getting with OpenACC, then we will feel more comfortable in moving our applications to OpenMP 4. So we have, since both specifications like OpenMP 4.1 and OpenACC 2.5 are kind of equivalent, or at least they're very similar to each other, we feel like we have from 2015 to 2017 to improve the OpenMP compilers for accelerators, and maybe at that point that's a good point for us to start transition the applications to OpenMP 4. So what do we need to translate things from OpenACC to OpenMP? Usually, the first thing that we need to do is to normalize the OpenACC application so that we use directives that are supported in OpenMP 4. So for example, we ask the users to change the ACC kernel directive to ACC parallel, so that, for example, that directive that has a correspondence in OpenMP. The same thing, we ask them to put it in the form that is easy to convert from OpenACC to OpenMP. We also ask first to start changing things, the data directives, and then those are more like a one-to-one mapping between OpenACC and OpenMP 4.1. Then move towards the parallel directives and eventually go to the subroutines directives and then convert the runtime APIs. So if we kind of like follow these sort of steps, we see that it's easier to move the code from OpenACC to OpenMP 4. To be more precise, when we say about what are the existing constructs in OpenACC which are not equivalent in OpenMP 4, this is OpenMP 4.0, because that's what the compilers that we have right now. And some of these will go away when we have OpenMP 4.1 implementations. So, but currently we have in OpenMP 4, we have we don't have a dynamic data regions, and the kernel's directive needs to be transformed. We have to take them out to convert it to ACC parallel. And then there are other things that we see in OpenMP 4.1, but we don't have it in 4.0. So if we start, for example, changing some of these to the supported features in OpenMP 4, then we will make easier the translation. So once we do that, we can translate the data regions, where we translate, for example, the data regions, the data declare directives, and all the clauses associated with it. Scalars needs to be converted to first private, as in OpenMP 4.0 is map to and from. And in some cases, when we use async in OpenACC, we may be able to use tasks to handle, at least emulate the behavior of async in OpenACC, although in OpenMP 4 there is still not a good correspondence yet. But there is a way to use tasks to at least exploit some asynchronicity there, and then replace the different device numbers to the clauses that that you specify from ACC device number to device num in OpenMP. One thing to note is that here we're putting things in terms of p copy in, p copy out, and that's because in OpenACC 2.0, that's the correspondence that we have with OpenMP 4. But in OpenACC 2.5, the default behavior of copy will be p copies. So that will make it easier for translating the codes from OpenACC to OpenMP. Then the other step is just to translate the update directive, so the target update, and then that's kind of like a straightforward. And then we can also use, replace also the async with the tasks, and that will be more helpful. Now, this is the more challenging part. So that part, the first and the second and the third step are very straightforward. It's very easy to do. Now, the challenging part is when we starting to translate some of the directives that describe the parallelism and also how to map it to the architecture. So, for example, we have ACC loop gang, or ACC loop worker, or ACC loop vector that probably can be translated to some of the directives that we have in OpenMP, like basically target teams, distribute or parallel for, or SIMD in a similar form. And the idea is that this mapping, because there is already a hint in terms of how you want to schedule the loops to the underlying levels of parallelism, then there is a kind of like direct translation to OpenMP 4. The most challenging part is the translation of something like ACC loop independent, where it is left to the compiler to pick what is the schedule that we need. In this case, it could be teams or parallel for or SIMD or any permutation of this, or any of these combined directives. So that could be teams distribute, parallel for SIMD or any of those directives. And then that's the piece where the programmer has to make the choices. And this is also gonna be the piece where it will depend on the architecture that you may want to target. But we're trying to understand how we can write OpenMP in a form that is also portable. without sacrificing this decision made by the compiler in OpenACC. And then we have these clauses where we can translate very easily the gang to this schedule, number of gangs to number of teams, number of workers to thread limit, vector length to safe length, and so on. So these sort of translations can be done, and then, but the hardest part is just how to translate the parallelism from a descriptive form into a prescriptive form in OpenMP. So there's going to be a lot of decisions that we will have to make. And then we have the ACC routine, which can be translated to the declared target. And in OpenACC, the routine, you can specify the level of parallelism, gang, worker, vectors, sequential, and we don't have that in OpenMP. So we assume that there is no need the compiler will automatically generate the different versions for these different levels of parallelism. And the challenge is mostly making sure that whatever you call the function has the right level of parallelism from where you are calling the function. And we hope that the OpenMP will help us to do this more easily to program in terms of GPUs. So this is one of the first examples that we use. So I translated basically 14 benchmarks from OpenACC to OpenMP 4, and I'm just going to go through some examples of what we did first and what led us to some success and what were the challenges. We see a lot of application users writing code like this where we have loop independent on different loopness levels. And at some point, we have to come up with a decision on how to translate it to OpenMP 4. And there are like several versions that we can write. So some users, when we ask, for example, several applications users to translate this piece of code, for example, some came with this version, which is basically just add a parallel 4, a target region and a parallel 4 in the outer loop, and then an SIMD in the inner loop. But we figured out that that may not be portable across architectures. It may work only for certain architectures like the Xeon Phi. And so that was, for example, that's one way of doing it, but might not be efficient for GPUs. However, we can write, another user attempted to do this transformation when they translated OpenACC and then uses nested parallelism. And in this case, the code was able to run, but it was probably not as efficient as before. And this is, some people thought that when they were going to write codes for the GPUs, that because GPUs may not have very good support for SIMD directive, that this was probably the right way to write it. But we figured out that probably is still not a portable OpenMP code because it might not run very efficient in the GPU. And yes. 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 Yes, yes, yes. So, yeah, so what happened was like, when we asked the people, some of the programmers to translate this for Xeon Phi, they were just thinking about, how to write it in Xeon Phi mainframe, and this is what they came up. And then we asked other people to think about GPUs, and then they thought, okay, maybe because GPUs they were not very clear what was the level of support for the SIMD directive in the GPUs. They were kind of like writing it this way, where you have like nested parallelism. But we know that nested parallelism, if not implemented efficiently, doesn't give performance, but this was just another form that people tried to write. And then we had this one where basically we could write, for example, this OpenMP version where we can start using the concept of teams distribute parallel 4, where basically that's more performance portable for the GPUs. But at the same time, users were specifying in the inner loop the SIMD directive. And what we realized was that that this pattern of writing OpenMP will make sense if the loops were not able to collapse. But some people, but basically, some people thought that this was like portable OpenMP, but there still needs some work to be done in this version because some of these loops can be collapsed and we can put everything in one combined directive. But that was another version that people came up, and unfortunately, this version, the assumption is that we hardwire the schedule in the inner loop as to be SIMD, and the two outer loops are teams distribute parallel 4. So it gives some flexibility to the compiler, but not for the inner loop. So for us, it was better, for example, if we, to write it as the most portable way was to really collapse all the loops in the loop nest and then write and use the combined directive, where we do OMP teams distribute parallel 4 SIMD. And that will basically leave the compiler the best choice on selecting what's the best way to schedule things in this case, the GPUs or the Xeon Phi. However, one thing is that when we start using a directive like this, and we look at the OpenMP specification, we notice that if we program this, we will leave the behavior of the compiler to be implementation defined, basically to select the number of teams or the thread limit or the safe length, for example. And if we don't have a good implementation, basically to select these features, we will have to specify them in the directives. So one of the challenges, one of the lessons that we're starting to learn is that it is very important for the compilers that use OpenMP 4 to target multiple accelerators or different heterogeneous systems to be smart about selecting, at least making an attempt to select how to map this for this loopness to the different architectures. And that's kind of like, that will kind of make life easier for Open ACC users, because then the compiler will help them to really write more portable codes. So the challenge is here to make sure that we put OpenMP in the right form to give as much flexibility to the OpenMP compiler to the optimizations. We are also not specifying a number of threads or assuming that the compiler will help us to identify what's best here. So we did other transformations with some other codes, and it was a very straightforward translation between OpenACC and OpenMP 4. Some of the cases, we were translating, for example, ACC parallel loops into the combined directive here. And one thing that we noticed is like, yes, the combined directive can be very long. Maybe in the future we can make it shorter or figure out another name that we can give to this combined directive will help the programs be more compact in the translation. So that was one of the codes that we did. We did another one where we have like similar patterns where we were able to translate them from one directive set to the other one. And when we did this comparison, we were able to get, in some of experimental compilers that we have, we were able to get similar performance. However, we still need to understand a little bit more how the OpenMP compilers are going to be mapping, or at least translating these combined directives into the architecture, and what choices are they going to make, or what optimizations they're going to make. So when we use this methodology, we successfully ported several benchmarks. Functionally, the benchmarks are correct. We found that the main challenges was the performance portability. There is a hope that OpenMP can leave a lot of freedom to the compiler by using the combined directives without specifying the number of teams or thread limits or length of the vectors. And because we see that, for example, GPUs are going to be sensible to number of teams or number of threads, and C-on-5 architectures are going to be more sensible to the length of the SIMD. And basically, we have to find the balance basically on how to write the code. In some cases, when we converted from Open ACC to OpenMP 4, for example, for a different architecture going from a GPU to a C-on-5, we needed to do some loop interchanges to exploit more SIMD in the C-on-5. And it would be nice to have a mechanism where we can probably trigger that sort of interchange so that we can, or a way to, so as a way to understand where it makes sense to use SIMD in the loop nest. Another thing that we came across was that there may be a need to write macros so that you can tune in different OpenMP options that you may have for different architectures if the compiler doesn't do a good job. And then one of the main macros that we hope to use is the collapse whenever to play with different collapsing levels. And then for all the different schedules, which are the number of teams or thread limit or distribute schedules or SIMD lengths, for example. Yes. Mm-hmm. Yes.
You also rely on the compiler and smart to decide what to do.
Yes.
I thought it was the same issue for both sides.
That's correct. That's correct.
They'll get it just as wrong.
What?
They'll get it just as wrong on both sides.
Right.
But yes.
So that's what I'm saying. This point applies to both compilers, not just OpenMP.
Yes, that's correct. Yeah, so the implementations, what happens is like, we are starting to understand the OpenMP 4 implementations as we're starting to see implementations for GPUs and C-on-5s. And so for example, one of the first implementations may not be that smart, and that causes the problem, may not generate performance portable codes, but as implementations improve, maybe there is if they catch up to the level of the same thing that OpenACC does, at least there is some base level that the user can use before tuning their code to something more specific to the architecture. But yes. So, yeah.
Another for we are fine and sensible for example, that's true.
Mm-hmm.
But this is also sensible for some GPU, not the immediate GPU. Immediate GPU is SIMP architecture. Right?
Yes.
For the ARC GPU, which has SIMP architecture, like Intel, GFX, and MP is an APU, right? You know,
Right.
the low level still SMP
Mm-hmm.
is also sensible for those GPU as well.
Okay.
So actually, NVIDIA wants, you want to do the SIMD loads, this is work for NVIDIA as they are for the other GPU.
Right.
If you don't coalesce your loads, you're dead in the water.
Sure, yeah.
So it's still, SIMD is still the main
Yes.
trick that a compiler can use.
Yes.
I agree, yeah. So it's not just,
Mhm.
my point is not just for sensible, yeah.
Yes, yes. So this is just, for example, our initial experiences, but of course we have to understand more as we experiment more in terms of mapping OpenMP 4 into different architectures. So these benchmarks that I just talked about are the spec ACCEL benchmarks, and we think we're going to be releasing them very soon. However, we're basically, this is going to be the first test that we're going to have to see how OpenMP can be written as portable as possible across architectures, and there's going to be a lot of feedback that we're going to get back to the community, to the OpenACC.
Based on your experience, to me it's intense.
Functionality, yes.
The functionality goes on more or less on top.
Yes, yes, yes.
Now it's go to the next level, thinking about how to get the performance and performance.
That's correct, that's correct. So the next step is to get the performance. And the reason why we don't have performance numbers here is because across architectures, at least in GPUs, the implementations are still not that mature yet. So we get functionality, but not yet the performance. And of course, we have CM5 implementations, but in our case, we wanted to understand OpenACC, we only have OpenACC for GPUs, to understand how those OpenMP looks for GPUs. And we will get more experience in that area as we get more compiler support.
One thing I want to point out, the safe part is the semantics guarantee, it's not a performance guarantee. And in the 4.1, we had another class called SMP length, also for the groups.
Mm-hmm.
That probably is a sensible for the performance. But
I see.
safe line is only guaranteed the semantics guarantee, correct?
Okay, yes, yes. So this is another piece that we will be experimenting, yes. So another thing I want to mention is OpenACC has been around for 3 years or so, and OpenMP 4 and 4.1 are starting to emerge the implementations for GPUs. So one question is, what has been the roadblocks of OpenACC, basically on how that we have experienced over the years that we need to put into OpenMP so that you don't suffer the same things that we had in OpenACC. And one of the main challenges for using OpenACC on Titan was the idea that we don't have like that great support for deep copy in terms of directives. And it's possible to do it using some of the runtime APIs, but that was one of the main challenges, at least on the Titan system, because we have a set of data structures that the user wanted to move certain elements or some to the GPU, or basically copy certain elements of the data structures and deeply nested data structures. And that's where things have started to break down in terms of using OpenACC. And those were for users that didn't want to restructure the data structure in their applications. So we had codes that were like very large in terms of code sizes, that changing the data structure will mean changing the entire application. And for those cases, the challenging was to get a good sort of deep copy support. And I think that OpenMP is already moving in that direction, which is very important for using the the directives, and now that we have more unified memory support, maybe this is going to be needed only for performance, but it's an important thing that we need to support in OpenMP 4 or 4.1 or 5. And then the other thing that people are starting to ask in terms of OpenACC and OpenMP is like, how are we going to be supporting different types of memories? How are we going to deal with this heterogeneity of the memories? Are we going to be required to use vendor-specific library calls, or can we put something in?
I think this is a good point, because for NVIDIA architecture, they have the scratch pad memory.
Yes.
Which is fast memory. And for our CPU, for our GFX architecture, we also have some fast, what we call shared local memory, which is the exact. So we need a library expansion to see how to tag those kind of memory, so the compiler can generate the code to put the memory application to the fast memory.
Yes.
Yeah, we actually for the accelerator-based next week we'll talk about
Yeah.
OpenMP 4.0.
Yes. Yes. Go ahead.
Just a quick question. As you develop OpenMP 4.1, we're very interested in the question of whether you're applying this to the Knight's Landing and beyond only, or are you also applying that to the Knight's Corner? The reason that I ask that is because we're actively using the largest Knight's Corner-based systems in the world, both at the NSF Supercomputing Center in Texas, MP1, and also we have access to MP2. And the efficiency on running beyond 1,000 processors is very, very good. Having to deal with offload mode and things like that. So the question is OpenMP 4.1 ready for deployment of practical problems right now?
Yeah. Well, so our main focus has been mostly on GPUs. We have, although we want to achieve portability for nice landing architecture, and but we think that in our case, OpenMP 4.1 will solve a lot of issues for us, at least for the GPUs. We will still need to understand how we will be writing portable code between GPUs and Xeon using OpenMP. That's an open question that it will depend a lot on the implementations of the compiler and also experimenting more on the model.
To Matson's right, you just write it for the GPU and it runs well on the PHYs, so you're done.
Yes.
That's what he tells us.
Yes, but we need to get the data, the real data, and then and this is something that we're going to be getting very soon.
Well, lots of things he says turn out that way.
Yes.
Yeah, the OpenMP 4.1 and 4.0 offloading model can be used for both the
Yes.
The difference between the KNC and KNL, the KNL manufactures the host and the card as a unified asset, right?
No, yes, already done. Okay. Yeah, because it's already time. Yes.
Host and the accelerator is up, because that is an animation for then when the word offloading and stuff. It's really up to your application, but in terms of OpenMP offloading model, we are going to support it for both KNC and KNL. But in KNL, a lot of the compiler burdens are removed because the architecture, the instruction set is included. We have an online removal and memory load and stuff like that. There's a lot of the compiler burdens are removed. You can get better performance with less, sensitivity on the SMP part, especially with the line and memory transfer.
As you know, the Canada 2 has a particularly challenging version that we have to deal with. So many of the Xeon 5s with one host processor. It's just a pain in the neck to figure out how to do that.
That's why we provide those many nodes now.
Right.
We provide those nodes.
Right.
My question was just that
Yes. Yes.
Any code
The-
you wrote for the transaction Stencil or running on that, I'd love to recompile, we can run it on the
Yes. Yeah. So OpenMP is a model, and the accelerator model is just one form to write OpenMP, but it should be portable across architectures. And then the other thing is that we have a lot of C++ applications, and we have so much resistance of using OpenMP in those C++ applications because they tend not to like the directives because they have things like templates, inheritance, STLs. And maybe there is another approach that we have to explore about how to go about OpenMP for C++, especially for accelerators. And now we have a better hope for tools. The other thing is just how to measure performance in the application, and now we have a tools API on both standards, or at least a technical report in OpenMP 4.1, at least that works with OpenMP 4, and we have one now in OpenACC 2.0, so that will help us to really understand more the challenges of the performance portability across architectures.
Right. So the last point, we have a lot of C++ programs that really like to do lab math.
Yes. C++ 11, yes.
We had a lot of discussion with those people. Currently, my understanding is C++ language completely people is after some library-based syntax to deal with this parallelism, right? With the fragment policy, parallel policy, so there's something proposal going on.
Okay, so yeah, the C++ committee has these two technical specifications, what we call parallel technical specification and technical specification for concurrency. The parallelism technical specification is actually somewhat based on the NVIDIA library thrust,
Yes.
in which you can create sequential or serialized versions of standard template libraries like sort and transform in and things like that. And in there, you could also optionally put in a vendor-specific one, say do this on the GPU. Now this is
Right.
a library. That's actually not bad.
Mhm.
That's okay as a start, but you can't really optimize these things. It's kind of okay if it's in the library.
Yes.
So to answer your questions about C++ for accelerators, one way that people have thought about directly translating OpenMP fragments into C++
Yes.
is using a system I had invented
Right.
in C++ 11 called C++ generalized attributes.
Okay.
The attributes attach to every single possible entity there is, including templates, namespaces, everywhere.
I see.
So it is possible to do it if you want a direct translation of
Right.
an OpenMP pragma system.
Right.
That's not how C++ is going to work.
Right.
I'm actually chairing another group called SG14,
I see.
which is responsible for games development and low latency. And we're exploring possibly some form that integrates C++ and OpenMP accelerators, OpenACC accelerators, OpenCL, and Vulkan,
I see.
which is the new way of doing OpenGL
Yes.
as a way of generalizing access to the GPU
Right.
to GPU accelerator,
Right.
accelerator resources.
Right.
We think that that's one way of doing
Yes.
it, but
Yes.
that work is still just
Right.
starting right now.
Yes. We already ran out of time, but just as a feedback, OpenACC is currently used mostly for Fortran in our codes, but we have very limited support for C++, and we need to look for a solution for accelerators in terms of C++, and I'm very interested in the effort that you're doing. And then this is just the summary, just like these two specs are really similar to each other. Right now, just to move for us from OpenACC to OpenMP 4, we just want to get the compilers, give us the performance, and help us to understand more how to write OpenMP 4 portable codes. And once we feel like we reach to that point, we will be asking the people to move to OpenMP 4. And then there are other things that needs to be explored, like multiple accelerators, but these are other things that will come along the way. And then, for any questions, just you probably already asked them. So,
Hopefully there's no more.
okay.